And welcome back to our end of the week lecture for Thermodynamics. This is just a quick reminder that next Wednesday we're going to have a quiz. That would be quiz 3. You have reading assignments for Koretsky in Chapter 3. You have supplemental reading specified on Canvas announcements and elsewhere for Kondapudi Chapter 3. You can find that in the library resources. I want you to pay specific attention to the Prigogine formalism, where we split up entropy change into DIS and DES, right? The internal entropy change and the entropy exchange, E for exchange, across the boundary. Last note on the adiabatic processes is that we're familiar with an adiabatic process as PV to the gamma equal to a constant. When we solve problems for that, we set PV for state 1 on one side and PV for state 2 on the other side of the equation. What you're seeing here is just if I were to use the ideal gas equation of state, PV bar is equal to RT, I could swap out any number of those variables, just like TV bar to the gamma minus 1 is equal to TV bar to the gamma minus 2. That's found in Wikipedia. You could do that yourself, but I'm just pointing out that you have a lot of resources out there. Another reminder, gamma is basically the same thing as K throughout our lecture notes. It's just like a quirk between different textbooks and web resources, but it's basically the same thing. Gamma is going to be CP over CV. Let's move on. So, just as a reminder, when you're looking at a cycle is a loop of 4 different processes, process A, B, C, and D, going from state 1 to state 2, that's A, state 2 to state 3, that's B, state 3 to state 4, that's C, and going back to where you started, state 4 to state 1, that's D, process D. For an irreversible cycle, the delta S of the surroundings, or of the cycle, is going to be greater than 0. We're always going to dissipate heat with an irreversible cycle. However, if you are looking at the idealized process, the Carnot cycle, for example, delta S of that cycle is going to be equal to 0. This is all reminders from last lecture. For your applied understanding, I strongly recommend you to work examples 3.2, 3.3, and 3.4. Work them by hand. I'm not talking about reading and looking for comprehension. Start writing them down. While you're doing that, look for the role of heat capacity in all these hypothetical paths. These are really good problems to deal with the ideas of hypothetical paths. Also, note the extensive use of the first law. We may be dealing with the second law, but we're using the first law quite a bit throughout these problem sets. And then, last note, I've got table 2.2 up there because, if you haven't noticed it yet, chapter 1, chapter 2, and chapter 3 are all tightly linked together. They go back and forth. They are the foundation of a lot of what we're thinking about in thermodynamics. Here's table 2.2. If you look at Q, you'll see that Q is fundamentally related to the second law of thermodynamics by the Clausius inequality. And all that I'm doing with the Clausius inequality is basically dq divided by t. So if I find a Q term and I divide it by t, I get delta S for, say, an isothermal process, which is going to be negative nr, natural log of the final state P2 over the initial state P1. Look right next to that equation, you'll see that we've got positive nr, natural log V2 over V1. And that's because there's a reciprocal relationship between pressure and volume. When pressure goes up in a chamber, the volume goes down. Okay, so we get the other side of things, which is the 2 examples for processes, for constraints on processes, where I have a hypothetical path that's either isobaric or isochoric. I'm going to use heat capacity because if I have an isobaric or an isochoric process in a hypothetical path, the only thing I can do is raise temperature, and that's going to go into an increase of entropy in the system. Whether it's compression or whether it's expansion, I have an increase in temperature. And you want to look at those figures in Chapter 3 to see what I'm talking about, or to review materials from the last lecture. All right. So if I were to think about thermodynamics as an energy conversion device, this is the end of the lecture last time. I said, hey, there are a couple of things you just cannot do in thermodynamics. Now, I described first Clausius and his research in 1865. He described, that, hey, heat cannot pass from a colder body to a hotter body. You don't get a bowl of soup to spontaneously get hot. If you want to get a bowl of soup hot, you put it in a pot over a heating coil or a hot pad, or you put it in the microwave. And in either case, you are compensating that system. You are putting in energy to raise the temperature from hotter to colder. So heat cannot pass from colder to hotter without compensation. I can't get a soup to go warm without a microwave. That is my energy heat pump that I'm using to pass energy from cold to hot, and it's essential to modern thermodynamics. I will note that the Koretsky text misses this, and that's why you're hearing it here in your lecture notes. Now next, we said, hey, Lord Kelvin, Max Planck, both worked on ideas of heat engines, of like ideal, best case heat engines. And they both found out that, look, it's impossible, totally impossible, to make a heat engine, to make an engine that only produces work out. No matter what, you're going to have Q losses. You're going to have Q. It's impossible to make a heat engine with no Q, with Q equal to 0, no dissipation of energy. So you can have a best case idealized Carnot cycle. You're still going to lose heat to that heat engine. You're still going to have heat that transfers across the boundary. And these two things are basically called the impossible heat engine on the bottom. And to pump heat up from colder to hotter, to move heat from cold to hot, you need a heat pump. And to have a heat pump move heat with 0 work, that's an impossible heat pump. To have a heat engine that only produces 100% work, that's an impossible heat engine. All right? Let's take a look at how that looks when we do some analysis on this. We would call these two ideas perpetual motion machines of the second kind, right? Perpetual motion machines, PMM, perpetual motion machines of the second kind is what we're looking at. Let's draw an energy conversion device. I'm going to draw my first energy conversion device, and it's going to be, this is where things get cool. When things get cool is where I use an energy conversion device between a source, a reservoir source, and a sink reservoir. So my source reservoir, let's assume it's cold, right? And my sink reservoir is hot, okay? I'm going to use the energy conversion device to move the heat from Q cold up through the energy conversion device and into Q hot. Okay, so I go from 1 to 2 to 3, right? 3 different bodies. And I'm using my energy conversion device to do that. But do you notice something? There's no work going into my energy conversion device. Another way to look at this, which is like the simplified version, is that you can't have something cold going spontaneously flowing energy into something hot. We would call that a Clausius device. So this idea of going from cold spontaneously to hot, we would call it a Clausius device. It's an impossible device. It doesn't happen. It's a perpetual motion machine of the second kind. I'm going to remind you here that this is, I think, the third time I've said this, that we have an absolute temperature scale out there. It's an object fact of nature. And ultimately, we had another researcher, Clapeyron, doing analysis of the Carnot cycle and finding out that, yes, Q can be directly related to T. Q2 over Q1 is directly equal to, under absolute temperature scales, T2 over T1. For an irreversible process, that would mean that the ratio of Q1 over T1 is going to be less than the ratio of Q2 over T2 because there's heat dissipation that's happening going from state 1 to state 2. So let's think about what did Clausius say? Okay, so Rudolf Clausius says, okay, it's impossible to make a device to engineer a device, an energy conversion device, where the only effect of that device in a cycle is heat transfer from a cold reservoir to the energy conversion device, and then up into a hot reservoir with an equal quantity of heat, right? So this is, heat transfer from a cold reservoir to the energy conversion device, then transfer by heat of an equal quantity of energy from the ECD, the energy conversion device, to a warmer reservoir. This is an impossible heat pump. Heat pump, right, takes low energy, moves it to high energy. It's an impossible heat pump because there's no work getting the job done. This is like imagining that you have a refrigerator that will cool your vegetables without being plugged into an electric circuit. There must be compensation. Compensation is the word of the day. Compensation will be the work input that moves energy in the direction that it would not have spontaneously gone. Feel free to pause, take a moment, think about this, go back to your reading. Some of the best reading of this is between the Kondapudi reading, but there's some great reading in DeVoe. The book that you used in the very beginning of class, DeVoe's Thermodynamics, has a great section on this as well. All right, so the next version of this is the perpetual motion machine of the second kind. I'm going to draw that same kind of energy conversion device and a cloud here, right? And in this particular case, it's again the second version of the perpetual motion machine of the second kind. I'm going to have a big source, a reservoir of hot air, hot something, hot fluid, and I'm going to dump Q across from 1 to 2 into my energy conversion device. And I'm going to assume that I get work shooting out of the right to 3, and I get 100% work coming out of there. Okay, this is the Kelvin-Planck engine. And if I say engine, I mean heat engine. So again, we got a relationship between Q and T to understand what's going on here. And if I look at what Kelvin and Planck together, what the statement is, what's impossible. What is thermodynamically impossible is it's impossible to make a device, to get out there and engineer a device, an energy conversion device, whose only effect through a cycle is heat transfer from a single hot reservoir to the energy conversion device and then on out with an equal quantity of energy as 100% work to the surroundings. Can't do that. We would call that a problem because there's no heat losses, there's no dissipation of energy, and it becomes an impossible heat engine. So I've got 2 perpetual motion machines. One is an impossible heat pump. The other is an impossible heat engine. All right? Now, cool thing here. This is both second law stuff. Perpetual motion machines of the second kind are second law perpetual motion machines, PMMs. So let's look at this. I'm gonna do some quick kind of analysis of these guys. I'm gonna add in for fun a Carnot heat engine or a heat pump. This is, again, information you could find in the reading from DeVoe if you wanted to go dig into it, but I'm just bringing it up right here in the lecture materials. So if I recall the heat engine, that's HE for heat engine, efficiency, my efficiency calculation is going to be 1 minus T cold over T hot. Let's draw that out. I'm going to do a very simple device where I just spontaneously have T cold going up to T hot through my energy conversion device. That would be a Clausius device. Okay, Clausius device is like this impossible heat pump. Then I'm going to plug, this is like Tinker Toys. I'm going to plug together an impossible heat pump with an ideal heat engine, a Carnot heat engine. Now you notice how I have 3 units of energy that goes up into my Clausius device, and then 3 units of energy goes out of my Clausius device, right? Whereas in my heat engine I have 4 units of heat that go in, 1 unit of heat that comes out, and 3 units of heat that comes out. 1 unit of work that comes out, and 3 units of heat that comes out the bottom on the Carnot engine. I'm going to use that. I'm going to do some basic math. Okay, so let's add those guys together, and what do I get? Well, what I get is, if I do the math right, is I'm going to get a surplus of 1 T hot going into the system, and 1 unit of work coming out of the system, which is diagrammatically a Kelvin Planck engine. So if I combine a Clausius device, an impossible heat pump, with a Carnot engine, I get an impossible heat engine. Let's flip that around. I'm going to take a Kelvin Planck engine and I'm going to combine it with a Carnot heat pump. So there's my Kelvin Planck engine on the left. I get 1 unit in, 1 unit of work out. There's my heat pump where I put 1 unit of energy in and I move heat from a cold to a hot reservoir. Do the math again, start adding these guys together, and I am creating a Clausius device. You might want to pause here, think about what I just did in these diagrams. You can feel free to go to the DeVoe chapter on this as well. But what the ultimate meaning is that both the Clausius statement for a perpetual motion machine and the Kelvin Planck statement for a perpetual motion machine are equivalent. They're the same problem. You get the same problem when you actually plug together a Carnot heat engine and a Carnot heat pump. You get an impossible device out of that. You will ultimately get a Clausius device. So there's no way to couple together perfect instruments or impossible instruments to somehow make thermodynamics do what it cannot do. Thermodynamics cannot move energy around without work, and thermodynamics cannot produce 100% work without dumping a little bit of energy out at the end. Pretty key things, but fun in that when you're looking at this, you're seeing the way that one might look at the second law of thermodynamics as a designer, as an engineer. Okay? All right. Now, last thing I want to talk about, last thing, is going to be what would be the third law of thermodynamics. So there's basically 3 things you can't do in the world of thermodynamics. One is you cannot create a perpetual motion machine of the first kind, which is just producing work spontaneously for infinite amount of time with no heat. You cannot do a perpetual motion machine of the second kind, which means you can't do an impossible heat pump and you can't do an impossible heat engine. You know, arguably inside of an exam you can't say it in quite this shorthand, but those are 3 things, the 2 things. And then the third thing you can't do in thermodynamics, third thing you can't do, you can't go to 0. You can't go to 0 degrees Kelvin. It is impossible by any process, no matter how ideal, to reduce the temperature of a system, any system, to 0 Kelvin in a finite number of finite operations. Okay, that's the mathematical part of this. But essentially, if I wanted to get to 0, I would have to dump all the energy out of the universe into a second, say, pocket universe. And if you've been watching your Doctor Who, you know that creating pocket universes is a bad thing. All right, so let's draw this out and let's think about this just in case we want to look at this in thermodynamic sense of the energy conversion device. Okay, let's assume that I'm going to take energy from something hot, something above 0 Kelvin, use an energy conversion device. I'm going to create work from this process, and I'm going to dump the energy into a reservoir, but I'm going to be trying to get the reservoir temperature to go down to 0, right? What I'm actually creating is a Kelvin Planck engine, and I'll show you why. So if I look at the efficiency of this system, the work that I produce relative to the Q hot is still going to be T cold over T hot. 1 minus T cold over T hot, in fact. But T cold, what's the temperature of T cold supposed to be? 0 Kelvin, right? Well, 0 Kelvin would mean 100% efficiency, 100% work. 100% work is a Kelvin Planck engine, which is like impossible. So the third law of thermodynamics couples directly into the second variant of the second of the second impossible thing you can do in thermodynamics. So, you know, what we've got here is 3 rules you can't do in thermodynamics, unless you're Doctor Who, apparently. But the good news is almost everything else out there, space travel, you know, readily available energy use for society and the well-being of people and all around the world. All of that is readily available, able to do, and effectively more or less tied to finance. How much is it going to cost to do? But there are three things you can't do. You can't create a perpetual motion machine of the first kind, you can't create a perpetual motion machine of the second kind, and you can't get to zero. Other than that, you've got a lot of design options available to you. So that's what I've got for today, for the end of the week. I wish you well in your week. I wish you have a good weekend. Good luck in your homework problem sets. Keep us aware of what's happening on the discussion forums, and have a great day.